is. So I'm going to share with you some scenarios that kids were doing, and I want you to think about where the engineering habits of mind are in this short little video here. So what they've done is they found this little snail outside at recess time, and we had critter cages at the ready, and so they could bring the snail in. And part of the deal is when they find a creature outside, they have to be cognizant of the habitat where they found it so that they can recreate that habitat in the classroom so the creature's going to be safe and comfortable while we study it, but just for a short piece of time. And so what they're doing is they're putting together little booklets so that they can start to jot down their notes about what they're observing about this snail. And I did not tell them to do any of this. This was all their idea. So you can see systems thinking and how they're putting together the book, the creativity, and that they're thinking of how to document their thinking in a booklet form. The optimism, I didn't see any frustration there yet. The collaboration, how they kind of have this assembly line thing going. The communication, where they all agreed of how they were going to document what they're figuring out. The attention to ethical considerations is how they're going to care for this snail as they are observing. So let's move on to another little scenario. And these two little boys are working on getting a marble to go down a ramp. And they did not, how do I say, these two little boys were not best friends. They were not even good friends, but they really respected what the other one knew about how to get a marble system to work. And so they were able to stuff down their dislike for each other because they wanted to work with each other, because they could create this really cool stuff. So they were paying attention to ethical considerations because they knew they had to temper their emotions in order to work together. They were communicating with each other and collaborating. There was optimism in that it didn't work the first time, it didn't work the second time or third time. The creativity was it was their design, their challenge. They wanted to make this system work in this way. They wanted a downward slope to get it started, a slight incline, turn a 90-degree angle, go down, turn another 90-degree angle, and then go down. And you can see how they're using their understanding of force and motion by blocking the path of the marble to force it to make the curve. So here's an example of engineering habits of mind in the world of children. This works really well because they're very highly interested in this. And Piaget said years ago that this is really the fuel that ignites the process of figuring out a solution or the construction of knowledge. And he talked about this as error-informed experimentation, where kids try out their ideas, they test them, they observe the results, and then they refine their ideas and test it again. So what he was talking about all those years ago was developmental early engineering. It's always been with us. It was just like me not seeing where it was in my children's lives, and I was missing out. Another person that recognized this is Henry Petrosky, and he's a renowned civil engineer who is a good systems analyst person. He builds a lot of bridges in the country, but he also writes a lot of books about simple technology. I think he wrote a book about the pencil, the paperclip, the scissors, the toothpick, but he saw engineering in early childhood, excuse me, as when they're stacking cans, or when they're moving dirt and sand, when they're designing their own toys or revamping a game with different rules. That's engineering in the world of a child, and it's rooted very deeply in imagination, choice, and play. And when you look at companies like Google and Ideal, they are very playful because they find that so essential in innovation. They go back to their roots in childhood. They connect with their inner child, and they engage in this kind of engineering thinking again. A formal, simple definition by William Wolff, who was a I think, past president of National Academy of Engineering. He said, very simply, engineering is design under constraint. And some typical engineering constraints for adults are the laws of physics, materials and their properties, space, time, and budget. And for children, it's really not that different. They have to grapple with the laws of physics, the materials and their properties, the space that they're allowed, the time that they have, the availability of the materials, but their biggest constraint is opportunity. And that's something that we are having a hard time finding for our children in our schools. There's not much opportunity for this. Now, a lot of people think that kids can't handle engineering, but you may have heard some talk about executive function skills, inhibitory control, where they're resisting habits, temptations, or distractions, working memory, holding and using information in your head, moving it around, and with the cognitive flexibility, moving it around in your head. I talked a little bit about this. There's more and more research pointing to how this is so important to start developing at an early age, because they find children's executive function skills is a greater predictor of literacy success than phonemic awareness assessments. In fact, it's a greater predictor of success in all academic domains. And what kinds of experiences help executive function skills? And those are experiences that require strategy and reflection, logic and reasoning, problem solving, that challenge to hold in mind their previous belief while they kind of mess around with what they think, how it needs to change, and then to think about categorization. So that's by definition, engineering experiences do that all. And so if you are engaging children in engineering experiences on a regular basis, you're helping them to develop those executive function skills. The National Academy of Engineering saw engineering design as this great pedagogical strategy. And I think it was before they were talking about executive functioning skills. But here you see a photograph of, these are children who wanted to retell the fish in the sea. And so they had some characters to stand, wooden characters to stand in, but they wanted a dock for them to fish off. And then they wanted the house for the characters to build on. And then they needed a lake for the fish to be in. And so they have constructed their own materials to retell the story. So that's one way of integrating literacy. But the best way of getting engineering in classrooms is by marrying it with physics. If you have physics and engineering, you have the interest of the children. And what's great about physics is that it's producible by kids. They don't have to wait for an adult to do it. You don't have to worry about protecting a creature or touching anything hot or anything like that. Then the result of what they do is immediate. They don't have to wait. And if you plant a seed and water it, you have to wait quite a while for that seed to grow. But with physics, that effect is immediate, and it's observable. They can see it, they can hear it, sometimes they can feel a weight change. And then the kicker is when it's variable. And that's what keeps them coming back, and that's the engineering piece. And what you see is a first grade classroom that is equipped with a set of unit blocks and children giving access to build marble runs using the unit blocks and track to make those marbles move in different ways. So again, if you're worried about how kids are going to respond to these kinds of materials, sometimes you want to start with rule making and have the children be involved when writing the rules. How are we going to keep everyone safe? And if they have a part in creating the rules, they are very invested in holding each other accountable. And if they are helping in writing them down, they will drag somebody else over to the rules and say, see, we promised we were going to do this. Now, what we do try to do is help kids to rephrase things to keep things more positive. So instead of don't put ramps in the air, don't bang the ramps on the floor, you can help them think about things in a more positive frame of mind by saying ramps stay on the ground, put ramps down carefully. So that's kind of engineering language in a way as well too. With the interactive writing here, there's a lot of things that you can do to support literacy learning. This teacher wrote things in red, blue, red, blue, red, blue. And she wrote the names of the contributors of the ideas right behind. And some of the kids that are just on the very beginning understanding of how print works, they won't remember how to read it, but they'll know where theirs is. And they'll bring somebody over to help them read it, or they'll bring their parent after school and say, I helped write this rule, and they can read it together. And sometimes they start to make sense of print by reading what they have co-created together in writing. You have lots of opportunities to engage in high frequency words when you're writing them. When you come to the word on, I know some of you know how to write the word on. Who can write the word on here? So inviting children up to come in and write the word on, or the, or we, or up. And so again, they're very engaged in developing those rules. It's important to think about concepts that are developed through conversations that focus on reasoning rather than those right answers. And again, that's going back to forming the mind, not furnishing things, furnishing the mind. And then being okay with kids repeating the same action over and over and over again. That's their way of finding out the predictability. Is this always going to happen this way? Let me look at that again. Did I really see that correctly? That's that iterative behavior of engineering that isn't really solving a problem as much as helping them understanding how the properties of force and motion are working with the materials that the object that they're moving that affect. And so I have two photos here by Peggy Ashbrook. She is a columnist for Science and Children for Early Science, and if you get Science and Children, look for her columns because she writes very well for early science learning. And she has been doing professional development with teachers on ramps and pathways. And she didn't have unit blocks in a lot of places, so they brought in sponges for the kids to use as supports. Then to contain them, she would bring in bread boxes so that the kids could keep the objects more contained. But what kids start to engineer is they figure out how to make a marble turn a corner. So they're grappling with Newton's laws of motion. You're not asking them to name Newton's laws of motion, but they're figuring out how the laws of physics work. So they get a working understanding of physics in order to make things happen. And then before long, they're turning multiple corners. And then they have an idea that they're going to change the direction of a marble. And so they'll have a marble go down from the left to the right, then drop down, and then move from the right to the left. All of their ideas, these kids were teaching us all the different ways they could move marbles. One child had seen a monster truck rally, and then so he had the idea that he was going to create a system that allowed the marble to jump over a gap over two cars. Other children had gone to an amusement park and had the idea of getting a marble to turn a loop. And so they were very demanding that they had the right kind of materials to allow them to figure that out. And so I had to find something flexible enough for them to curl and a way for them to attach it to the floor. So we used the foam pipe insulation and Velcro so that they could tighten that curl. Then when space got to be an issue, we gave them real estate to work within. So how far could they get their marble to travel in just this narrow piece of real estate? And we found kids would start to build vertically to try to get the most mileage out of a marble. This is an example of a second grader that got a marble to travel 39 feet in a 3x3 foot of space. And when they first start to figure out the physics behind it, it's not very pretty, but once they start to understand the physics, their structures become more and more beautiful. The aesthetics start to get involved. The vocabulary that you are able to use with children is very powerful. And it's vocabulary that you don't typically run into in early childhood text, but it's a vocabulary that have to do with properties, motion, position, condition, and actions. And so this was one experiment where I had my university students record all the different types of language that they were using when they were working with ramps and pathways. And we were astounded at the variety and the diversity of language that they were doing. But at the very beginning, when kids are starting to figure this out, a good idea is to take a digital photo, print it out on paper, and then invite them to write what they were doing. And then this is an example of a child that knew to start left to right, but he didn't know that he kept curving it around. So it starts on the left, I was racing, and then the ing kind of goes to the left again. So he's kind of writing in a snake. So it's really interesting that you get a window into their conceptual understanding of how print works by their interest in writing about what they're doing. When kids don't have an understanding of a word, sometimes we ask them to tell me what you're trying to say, and they would say it, we would repeat it back, and then we'd count how many words they said, and then we would make yellow lines underneath. Okay, so here's where you write each word. And that helps kids to develop a sense of word. And before long, they start to document using conventional spellings, and start to pay attention to more mechanics too. Although we never assess them on their writing or in a formal sense, it more informed our teaching as a formative assessment, letting us know where they were in their conceptual understanding of print. Now, one of the things that engineering curriculum will ask you to do is to ask kids to draw before they build. And that's difficult to ask young kids because they don't have enough understanding about the laws of physics, and they don't have enough experience with properties of materials to know how that's all going to interact. So they might draw a plan just because they're obedient, but their plan rarely informs what they build. It rarely matches, but every once in a while it does. And so sometimes we invite kids to draw, but they're more apt to draw after they build it. But even that is difficult because it's hard to draw a three-dimensional thing with action on a two-dimensional plane. And so we try not to force that on kids. Here's a few more examples. Here's a little boy that was doing a top view in the orange on the right, side view on the green. And these were kids that were working with Peggy. Here's another examples that she had a child do. And so it's got a mixture of the adult writing down the child's words with the child's drawings to tell exactly what happened. And then this happened once. There was a child that drew a top view and a side view of her structure. And she emailed it to me. I said, whoa, tell me about this kid. She says, well, I have to tell you, her parents are artists. So they do a lot of drawing in the home. So the experience of drawing had a great impact on that. But blueprints, engineers do use blueprints. So how does that look at the very beginning? Because marble systems are three-dimensional. Here's an example that came very naturally with a little girl that was really interested in building ramps with hills and valleys. And she got really good at it to the point where she'd say, just give me a challenge and I will build it for you. So draw it out. And so we would start to do these linear blueprints for her, which started to help us think about left to right again. But then she would take the blueprint, use it, and then build the ramp system. And you see how incremental changes that they were making in the height in order for the marble to go over the track. But one time I decided I was going to make something that was impossible. And so I drew this as a blueprint, seeing what she would do. And you can see that the first hill, after it goes down, the first hill is much lower than the next one, so it's impossible to do. And those two little girls took it over to the blocks. They looked at it, and it wasn't like 10 seconds they came back, and they said, sorry, we can't build this for you. And I said, well, you told me you would build anything I wanted. I want this built. No, it's not possible because the marble's not going to have enough speed to get up. So they were explaining the whole concept. So we brought it to the rest of the class to see if everybody else was thinking that way. So we had a chance to talk about first and second in our print. And the kids had a whole conversation about the problems that you have in getting just the right elevation to get just the right speed. It's just amazing what kids think. Why is this all relevant? Because in the Common Core, it does talk about technical text, directions, forms, information displayed in graphs, charts, maps, and this is a wonderful context for making charts, and graphs, where they have to write a title, where they're labeling things, where they're sorting things, where they're classifying. And in the process, they're using beginning sounds to write the initial letter, and then they're comparing. Here's a little boy that's writing about his exploration in water. They're engineering water. These are little plastic cups with holes in different places in the cups. And so they're working together to build a water system to move the water from one cup to another. And after a while, we give them a pegboard and rings so that they can start to put the cups into holes, and then they start to build these fountains for one cup to drain into another. And you might notice that at the bottom of the one in the middle, there's a little tornado type effect that happens with water. They noticed that. And in the background, you might see a chart on the wall. When the water's high, there's a tornado, but when the water's low, then there isn't the tornado. It's amazing the details that they notice. Here's where they had a reservoir where we used an upside down liter bottle in a tube, and they figured out that they needed the reservoir in a high place in order to get it to work to fill the cups. And then the kids made the leap, well, that's why water towers are up high, is so that the water can come through the pipes. It's just wonderful when you put them in these kinds of experiences. Engineering soap bubbles, which might seem really, really trivial, but kids are interested in it. And here is a story of a child that is writing about what she's noticing. And notice how she's circling the words. She's not sure that she spelled them correctly. But rather than holding herself back, she's writing down in a logical way so that she can come back and fix them later. So that's a very healthy attitude towards writing and then taking risks in literacy behavior. These are sippy cups where we saw the bottoms off, and then we put different kinds of fabric on the ends of it with different kinds of weaves, and the density of the fabric affects the kind of snake that emerges, and that was very fascinating to them. But conceptualizing what was going on inside of a bubble, noticing that when she holds the bubble and puts her hands together, the air has to go somewhere, so the air reaches out at the top and the bottom, and how she can manipulate the air inside the skin of a bubble. Again, the literacy, documenting what they're noticing, what's the best way to make a bubble. Here's one where they were using macrame cord and tubes to make a film, and then noticing that they could make a bubble just by using the air in the room and moving the utensil. And then writing about this, where the kids were taking the bubble and almost putting it on like a hat. And if you notice, you see that inside is underlined and the AW and SAW. The kids got so close, used to observing that this spilled over into their literacy. So they started to notice patterns in how words are spelled and spelling patterns. It became part of their habits of mind. Okay. Now, to show how this is worthwhile, I ran across this story recently. There was this boy that was trying to get soap bubbles to spread on the surface, but they kept bursting. And then he noticed that once popped, the bubble doesn't disappear, but it creates a ring of miniature bubbles. And he asked why, and no one knew. And then he asked even more questions. Why do drops splash? And he had no answer. Well, this person went on to do some research, and he is now, I think he's a graduate from Harvard, and now his research is in the field of healthcare, looking at virus transfer via droplets, energy, working on boiling and condensation, and the materials are foams. And he says when he teaches classes, he could teach a whole course about bubbles. The more I learn about them, the more I realize how much we don't know. And so we have to stop thinking about what kids are looking at as frivolous. It's very rich material that we need to pay attention to. Another person is Stanford bioengineer that got a Genius grant to investigate bubbles. And I was listening to a thing on NPR with him, and somebody had noticed that when you added dye to the bubbles, where they joined, he said it's a perfect 120 degrees. The bubbles like to be in pairs of 3. If they can't be by themselves, they're going to be round. But if they can't be round, they want to be with 3. And I never thought about that until I started looking at them. By golly, it is. And there's always a 120 degree intersection because there's 360 degrees in a circle. Fascinating, isn't it? And even climate change, they're starting to study bubbles in climate change that have a lot to do with what's released into the atmosphere, and they're even finding tonal differences in bubbles that pop in waves that tell them about the condition of the climate. So here's a second grade classroom that is just starting to document things about bubbles on a wall. All the writing goes on the wall, very much integrated with literacy. I'm going to score ahead here a second here. I'm going to just give you a few other examples because I have like 4 minutes. Engineering rotational motion with tops is another engineering experience where they can write lists of materials that they're going to need. There's Noah, who hated reading at the beginning, but then he started to write, I made a top, and it actually spins, and it is 5 inches and 1/4, and then started to write more about tops. Chemical engineering with making pancakes, engineering pancake recipes. The more water in the batter will make a bigger but flatter pancake. Engineering pudding, the more milk is added to a dry mix, it becomes thin and runny, and the length of the time the pudding mixture is shaken affects the viscosity of the pudding. Even corn muffins, we would make corn muffins in the microwave, and they would adapt recipes until they would tweak it, and Aaliyah's was better than the one that we had come up with, and so everybody was using Aaliyah's recipe. This fits in with older children too. These are 5th graders that were doing an investigation on engineering a pancake recipe, which even involved investigating about when was the appropriate time to flip a pancake. Physics of sound. Are you making instruments as a craft when they could be an engineering challenge in looking at vibration with rubber bands and how the tension of the rubber band is going to change the sound? Where this can happen is during your regular science time, but I found that kids were so thirsty about it. We have schools that are doing this during small group reading instruction. Whereas what are the other 2/3 of the class doing while you're with small group reading? Most schools, they're reading to self, someone else, they're listening to reading, working on writing or word work. And so the kids are going back between guided reading and literacy. Well, we have added STEM investigations to this. And the kids stay engaged in their investigations, and there's a whole lot of vocabulary and talk and discussion at the end of the morning that leads right back into writing and literacy. So as you're just finishing up one small group instruction, this is going on nearby, and kids learn to work with the sounds in the room, with the acoustics, and everybody stays happy because there's that whole attention to ethical considerations. How many minutes do I have left? 2?
A couple of minutes, yeah.
Okay.
Yeah, I can see we could easily do a whole series on this.
Yeah.
This is really, really interesting, exciting work.
Yeah, but the last one was Airstreams that I was going to show. And the one little boy I wanted to talk about, they're making air tunnels. He was really good, but he really struggled with literacy, writing down everything that they were doing, but he really did not want to write. And it was even December, he was still not writing much, maybe just responding with a word. And in January, he would respond only to things that had to do with science. And then finally in February, he was all pumped up about making these air tunnels. And so I sat down with him and I did an interactive writing with him, where I wrote, he has a force of air center in his classroom, and then I handed the pen back to him, and he wrote, it has a ping pong ball. And then he handed the pen back to me. I wrote, it has a vacuum cleaner. So we did that until we had the whole story written, and every time we added a sentence, we would go back and reread it. And then he said, he went over it with brown marker, and then he asked me to make 5 copies of it because he was so proud of what he had read, and he wanted one hung up in the center. So to me, engineering and literacy, it's a no-brainer. It's this wonderful, natural way to integrate STEM and literacy.
Sort of a comment here. There is a common division between the grades in the school, and I found K through 2 is a real different area for teacher in comparison with 3 to 8. What do you think about that? Just in terms of like the difference between the sorts of activities the kids are doing and the environment in those grades.
Yes, I agree. K2 is focused almost entirely on literacy development and mathematics, and kids are denied science from preschool to fourth grade. And then so the children that excel in science but not necessarily in literacy experience failure for 4 years before they finally get back to science. And by then they're pretty beaten down.
Yeah.
And teacher prep focus mostly on the upper grades in science because they don't know what to do with the little kids. So it is difficult.
If you go in and you are interested in focusing on early elementary and pre-K and kindergarten, are you just not getting a lot of science instruction?
If you are, we're finding that our early childhood majors get a really full-bodied idea of what it is to integrate. But in Iowa, you can get your K-5 licensure and not take early childhood, which is unfortunate because they don't get that developmental piece of child development. So we try to get them into the region center as often as we can, and we're getting more and more curriculum classes that are coming down with their students to engage with these materials. And our area education agencies are starting to come as well, too.
I want to thank everybody for coming. I want to encourage you to, if you're not familiar with linkengineering.org, to go and check it out. That's a project of the National Academy of Engineering with sponsorship from Chevron. And it's just been such a pleasure. I think that we could easily do a series of many, many episodes of this wonderful work. So many ways to connect literacy and engineering, and obviously the two support each other really well. Thank you so much, Beth Van Meeteren, for joining us today. It was a real pleasure to meet you and hear about the work that you're doing. So thank you, everybody, and have a wonderful weekend and good holidays.
Thank you. Good night.